Greetings to all. My name is Kiwan, and I am a second year undergraduate student reading mechanical engineering at Heriot-Watt University, Malaysia. The title of my speech today is Keep Moving Forward, Lessons Learned from an Engineering Design Project. As a child, one of the most iconic films I remember watching was Meet the Robinsons. It was a computer animated comedy film produced by Disney in 2007. It revolves around a 12-year-old orphan named Lewis who can't seem to get adopted or make his inventions work despite repeated efforts. He begins to seriously doubt himself and his abilities as an inventor. Thanks to a chance encounter with a kid named Wilbur Robinson, he sets off on a time-traveling journey to find a family he never knew. In the fantastical world of 2037, hip-hopping frogs and dogs that wear glasses are as common as talking dinosaurs. In an amazing twist, Lewis discovers that the fate of the future rests in his hands, but he can't save it alone. He'll need every bit of help he can get from the wonderfully wacky family named the Robinsons, who help him learn to never stop believing in himself and to keep moving forward. Throughout the film, that maxim recurs incessantly, but it comes up prominently in one scene in particular. At this point, Lewis was invited by the Robinsons to have dinner with them. After the first course of spaghetti and meatballs and a ludicrous food war, the next course was peanut butter and jelly, shot from a nifty gun onto slices of toast from a distance. However, the gun got jammed, and Wilbur persuades the initially reluctant Lewis to attempt to repair it. Unfortunately, the gadget malfunctions and creates a colossal mess, covering everyone and everything. Lewis apologizes profusely as he expects the Robinsons to get angry, but then...
You failed!
And it was awesome!
Exceptional!
Outstanding!
I did better!
From failing, you learn. From success, not so much.
If I gave up every time I failed, I never would have made the meatball cannon.
I never would have made my fireproof pants. Still working out the kinks.
Like my husband always says.
Keep moving forward. Those three words have stuck to me like peanut butter stuck to the roof of your mouth after eating a PB&J sandwich. They ring even truer for me, especially in this past academic year, which I have completed fully online due to the ongoing pandemic. It seems remarkable to be able to work on group assignments and projects with group members living halfway across the globe without needing to leave the comforts of home. I shall recount a couple of anecdotes where to keep moving forward has been crucial. These anecdotes are all from one particular project I have done in this academic year, from what is arguably my favorite unit in this course so far, energy studies. Before we get any further, I would like to point out that I will loosely interchange between energy, power, and electricity, but in this particular instance, they all mean the same thing and have no discernible difference. In energy studies, one major assignment was for us to design and plan an electricity grid for an isolated island far from the mainland, which was looking at switching to 100% renewable energy. The energy sources available on the island were potentially from onshore vertical axis wind turbines, run-of-river hydroelectric schemes, and solar photovoltaic panels. There were 12 families, 18 couples, and 5 small businesses on this island. However, there was a catch. The island had no connection to the mainland. No electricity can be either imported from or exported to any other grid. All electricity needed must be generated on the island, and any electricity generated must be consumed on the island. It seemed we had our work cut out for us then. One major problem that we ran into was as follows. We were creating a model of energy supply and demand in order to simulate how our design grid could potentially perform, as well as help determine the energy storage required for times when energy demand outstrips supply. We had hourly data of energy demand from the consumers for one average year, as well as the hourly wind speeds and river flow rates in an average year. However, the data that we generated from the simulation package called PVSys for the solar photovoltaic cells were only monthly values. By this point, we had ruled out hydropower due to the geography of the island being unsuitable to build a dam, as well as the small flow rate of the rivers on the island. Therefore, we had to use solar and wind, the combined energy yields of which were substantial enough to supply the island. The difference in resolution in the data had put a spanner in the works. Initially, we had decided to create a model based on the daily data, converting the first two data sets and simply dividing monthly values from the solar data by the number of days in each month. However, this became a problem when it came to determining the energy storage required and its usage. This was so, as even if we were to consider the day as a whole as having greater energy supply than demand, there might be particular times within the same day where demand is far greater than supply, which gets glossed over when using daily values. This was a salient consideration for these following two reasons. Firstly, some energy was lost when stored, depending on the efficiency of the type of energy storage used. Hence the inherent assumption in using daily values that energy produced at one part of the day can cover an energy equal demand value in another was totally unreasonable. Secondly, certain types of energy storage that we were considering can only supply energy for a particular period of time, after which the energy storage needs to be recharged. Therefore, we were trying to ensure that the maximum duration that the energy storage powers demand is less than the maximum duration that particular storage option supplied. Thus, how were we to estimate the hourly values for power generated from our solar panels? We already had our daily values in each month, so then we started finding the daylight hours during which the solar panels produced power. However, we quickly realized that this could vary from month to month, and did some research for our particular reference location. As the yearly variation in daylight hours was only around 2 to 3 hours, we decided that we varied the hours by season. Another thing that we realized as well was that it was unreasonable to assume that an equal amount of power was produced each hour during the daylight period. Again, we did further research and found that the amount of solar power generated was a function of the sine of the angle of the sun's elevation. We did find that we needed to adjust our values by a particular constant, the variation of which through all the months in the year was not dissimilar to a cosine function. The thing was, all my group mates, bar me, thought that this endeavor was too time-consuming and not worth the effort, instead wanting to opt to explain the possible inaccuracies in the solar data in words, to quote one of them. However, I stuck to my guns and believed that with some elbow grease, it could be completed. Several hours of tedious data manipulation later, and we got the hourly solar data. It was no small feat, but it does goes to show that where there is a will, there is a way, and in this case, we were rewarded with a greater resolution in our model. Well, with that, we kept moving forward. However, another problem soon hit us. From analyzing the data, it seemed that the amount of energy we were producing in 1 year is far greater than what the demand can consume in that same year, and if it were all to be stored, then the energy storage would be rendered economically unviable. It soon dawned on us that we needed to find ways to reduce the supply and determine when to take our wind turbines and solar photovoltaic panels offline. Thankfully, the time taken for these to come online and offline were mere seconds, the deficit of which would be supplied by flywheels, our choice of short-term energy storage. At first, we decided to simply take some wind turbines and solar photovoltaic panels offline for long periods of time where maintenance work could take place. But then it soon became untenable due to the near erratic nature of the change between periods of energy surplus and deficit. Even the manual adjustments in the model soon became extremely tedious to do. With that, I suggested that we might automate the process of taking the wind turbines and solar panels and taking the wind turbines and solar panels online and offline and devise an algorithm for it. As the overwhelming majority of our power was generated from the solar panels, we only imposed this algorithm on it to avoid extra maintenance which could arise from taking wind turbines in and out of operations, and the blades cannot be abruptly stopped, but rather spin slowly until they do stop. The resulting algorithm had 5 steps, depending on whether the amount of stored energy is below the lower or upper thresholds, whether the generated power is greater than demand, whether the energy from wind exceeds demand, and whether in times when energy of wind is below demand, if there is enough solar energy. Depending on those variables, a proportion of the solar panels would be taken offline, the exact proportion of which would be computed. It all sounds very nifty, does it not? However, when we tested it on our model, we found that most of the considerations that I have mentioned had little impact on the effects we desired. Soon, that algorithm that we first had was reduced to only one step: whether the amount of stored energy was above or below a certain threshold. This goes to show that sometimes we overcomplicate things when really there is a simple solution waiting to be discovered. In essence, not to crack a nut with a sledgehammer, just keep moving forward. Although we had recourse to a diesel generator in times of small supply deficits, we were glad that we could design an electricity grid that only required it strictly during emergencies, and one with a reasonable levelized cost of energy of 28 pence per kilowatt hour, as compared to that of the real-life exemplar on the Isle of Eigg in Scotland at 20 pence per kilowatt hour. In conclusion, if at first you don't succeed, try again. This has been the key in keeping on moving forward, in my experience at least, and this experience has been vindicated by others as well. It is said that Thomas Edison, scientist and engineer extraordinaire, failed 10,000 times in refining the light bulb. When asked by a reporter, how did it feel to fail 10,000 times? Edison scoffed and curtly replied, "I didn't fail 10,000 times. The light bulb was an invention with 10,000 steps." Whether this story was true or apocryphal is immaterial. The lesson remains the same, that by moving forward, even if it is a misstep, you are still one step closer in succeeding than when you do not move at all. Thank you, and remember,